Yeah. So, okay, hello and welcome everyone to the 18th lecture of our CUDA programming. So, in the previous lecture, we saw things related to the function, right? So, we saw what are the different kinds of functions like host function, device function, then host device function, then global function, which is also known as kernel, and so on. And then we saw typical examples related to this different types of functions and yeah, and then towards the end we saw, we touched briefly upon what is Thirst library and what are the functionalities that it provides us. And yeah, there we ended with the previous lecture, and yeah, that was the outline for the previous lecture. So for the today's lecture, we are planning to look into the support aspects of the GPU programming. So we'll see what are the make files and first of all see what are the make files and how to write the make files, what is the structure of the make file and so on. And then we'll see one use case related to the make file use case related to the how to use make file for running the CUDA programs, that is compiling, running the CUDA programs. Then we'll see then we'll see the debugging aspect, that is we'll see how to debug our CUDA programs using something called as cuda-gdb, and we'll see some examples related to it. And then later we'll see what is profiling, that is uh, how to measure the time that is associated with our CUDA program, and and for doing that we'll see something called as nvprof, and yeah, there we'll probably end with the today's lecture with the profiling. So okay, so with this let's get started. Okay, so let me first see if there is anything. Okay, so there is nothing in the chat, and yeah, so okay, let us start with the today's lecture. So let us first of all see what are the makefiles. So makefiles are nothing but a set of commands which contains targets and variables. They are associated with targets and variables for compiling the object file and to remove them. So yeah, so in the typical makefile you can write targets in such a way that you create multiple object files and remove them, and yeah, this is typically helpful for the large project where you have a lot of it will save a lot of manual work because you can just write everything in makefile and then you can just run make. We'll see the examples related to it. And yeah, so moving on further, so makefiles are typically used when there are dependencies among files. So consider that you are handling a very large project, and there are multiple files, and let's say file a.cu has dependency on some two other files like c.cu and d.cu. So c.cu and d.cu first must be compiled first, and then only a.cu should be compiled. And once that a.cu is compiled, you should run some, you should compile and run some another file, another CUDA file, which is, let's say, hello-world.c. So if such kind of dependency is there, that can be modeled as directed acyclic graph, and you can typically use this make files for uh, resolving these dependencies, or I would say that you can write the make files to automate the execution of your, execution of automate that execution flow of your project. And yes, this is typically useful for the large projects where there might be many dependencies among the files. So the example that I gave was a very small one, but consider that you have a very large dependency tree, and there are a lot of dependencies going on. So for that, how makefile can help is that you just need to look and resolve those dependencies and write them in makefile only once, and you can run it multiple times. You can run it as many times as you want whenever you are running your project. You want to run run or demonstrate your project. So yeah, so you can just write it once and run it multiple times. In makefile you can write once and run multiple times, and it is, makefile is nothing but the set of commands. So yeah, we'll see with the example, it will get more clear with the example in the later slides. Yeah, but I'm assuming that this is clear, that it really helps in the case when there are a lot of dependencies, and in case where when we are working with a very large project. Okay, so moving further, once we have written this make file, which is just nothing but the set of commands or the instructions, we need to run this make file, and for that we have something called as make utility, and it's a command line utility to process the instructions which are written, or the commands which are written in the make file. And yeah, and yeah, and then we sorry, yeah, and then we put all the files or the necessary uh, things or files that are associated for running this makefile into the same directory or the current directory in which the makefile is present. So yeah, I'll give that example. I mean, we'll see the example towards the end, and it will get this line. I mean, this point will get more clear with that. Any questions up till this point? Let me quickly. Okay, I am assuming that we are clear up till this point. So let us move on. So yeah, so typical syntax or the typical structure of the makefile is, I mean, it looks something like this. You have targets, then you have prerequisites, which are separated by colon, and then there are these commands. So and you can have this. I mean, you can have multiple combinations. I mean, not multiple combinations, but uh, multiple such blocks which are known as rules. So this entire thing, which is targets, then prerequisites, and then followed by command, this entire thing makes a single rule in the makefile, and you can have such multiple rules inside a makefile. And now let us see what are this each and every things, what are targets, what are prerequisites, and so on. So yeah, so the target is nothing but the file that is generated uh, by this set of commands, or it can also be some action that you want to perform. So it can be either file name or an action. And prerequisite is nothing but the uh, set of commands or set of actions or set of files that are needed for this target or this set of commands or this target to execute. So let us say that as I gave in the, I mean, as I gave one previous example, right, that for running hello.cu, you might have some prerequisites. Let's say for running hello.cu, my requirement is such that I want a.cu and b.cu to already run before them. I mean, before that, before the hello.cu is executed, I want a.cu and b.cu to execute. So that whatever output that is dumped into some file, I mean, hello world might be reading from it. So in order to make sure that the correct file is being read, I want this a.cu and b.cu to run. So here a.cu and b.cu are prerequisites, and target is the our hello.cu file. So target can be hello and prerequisites can be a and b, which are the name of the file. So it can be either file names or can be some actions. So we'll also see, we'll see the examples and it will be clear. It can be actions also, and yeah. So and both of them are separated by columns, and then we have this set of commands or the series or the which are the series of the steps. So yeah, so here each and every command will be they will be in a very similar fashion to the way we write in our terminal. But yeah, we'll see this with the example. What are the commands and what are the typical commands that we use? I mean, that we can write here. So yeah, and one thing to observe here is that whenever you write the rule and whenever you are writing the command for a particular rule, it must be separated by tab. Otherwise, there will be some issue when you will try to run the make. So yeah, please note that the commands need to be separated with a tab character and not space. So this is not space, but it's a tab. Okay, so any confusion related to what is rule, what is command, target, and prerequisite up till this point? Okay, if there are no questions, let's move further. Okay, so let us see one very simple example related to the makefile. So here our target is hello. I think you can correlate. The target is hello, and prerequisite is nothing. which says that this target or the commands which are written inside this rule uh, can be run without any prerequisites. That is, this target hello do not need to wait for any of the any of the previous files or any of the previous targets. So yeah, so this hello world can this hello target can run, and what command it executes, which is the command it executes is this echo hello world. So whenever you typically write this thing inside the make file, and then when you run this make command, so one thing that you should observe here is that this entire thing, this whatever is there inside this white box, has to be written in the make file, and you need to place that make file in some current directory. So I hope that point that I'm trying to make is clear. So there will be a file called make file that you need to place in your some current directory in which you are uh, creating some project. So your project might be having some multiple number of files like hello.cu and a.cu and so on. And inside that, since these files might have some dependencies among them, and since you want to resolve, or you want to make sure that dependencies are met, you are writing this make file. Now this make file should be inside this current directory whenever you are trying to compile it. So this make file should be inside the current directory in which your all these files are there related to the project. And yeah, so whatever is this in inside this white box should be written in that make file, and this make file should be compiled using this make command. And whenever you run this make command, it will start executing from this point. So here it will see that this target hello can be executed without any prerequisite. So it will start executing the commands inside this hello target. So this rule will be executed, and it will print the output, which is hello world. Since echo, you people might be knowing what is echo command, so it will print whatever is there inside it. So it will print the hello world. So yeah, so point here to observe is that this entire thing will go inside the make file. We have to run the make file using make command on the terminal. And what are the things that are going on here? The hello is target, prerequisite is nothing, and this echo hello world is the command, and this entire thing is a rule. So I hope that is clear. So let us move further. So yeah, I think you people might remember this program that we saw in our initial lectures, right? That we are launching the kernel with just one warp, and we are printing hello world 32 times, and we were having the CDS. So let us try to write a make file corresponding to this CUDA program. So when I say let us try to write the make file, meaning we want to run this CUDA program. First of all, we need to compile this, then run this, and then once we get the desired output, we want to delete the binary file that is generated related to this CUDA program. So how can we do this thing? So quickly let us look into it. So yeah, so this can be one of the typical way in which we can compile and run it. And if you can see here, there are multiple rules here. Now please note that there is not just single rule here, there are multiple rules. Specifically there are 3 rules here. First is this this one, then this, and then this. So 3 rules here. And yeah, and let us see how are the dependencies that are being generated here. So here, first of all, we can see that there is some target called clean, but it is dependent on some blah. Now this blah is again dependent on hello, and then we come to hello, but hello is not dependent on anything. So first of all, what is which target will be executed is this, which rule will be executed is this hello. So this target hello has no prerequisites, hence this rule can execute, and this commands inside this rule will be executed. And yeah, what it generates, so what it does is it compiles this hello.cu file and generates the binary file corresponding to it, which is hello. So in this case, the name of target and name of file are same, so please note that. And once this rule is finished, now this rule can execute, right? Because it was waiting for the hello, and hello is already done. This rule is already, this one is already finished. Hence, this can execute. This block can, the target block can execute, and it will. What it will do is it will run /hello. So it will run this binary file which was being compiled. Which was being generated by compiling hello.c, and what it will do, it will print hello world 32 times, right? Because running this CUDA program gives us output hello world 32 times. And after that, what will happen? Since this is finished, this rule is finished, which was having target as block, this can now execute. This rule can execute, and this rule, which is named as clean, can execute. And what it will do, it will remove hello binary file using rm command. So this and so this hello world, this hello binary file which was created by compiling hello.c will be removed. So what has happened? We have compiled a small CUDA program, ran it, and then removed the binary file after running it. So when we so please note that this entire thing is inside a makefile, and please note that this program which was hello.cu was also inside the same directory. So again, this makefile and this hello.cu were inside the same directory, and what we did was we ran this. We kept all these things in that makefile, and then we ran make. And what it did, it compiled that hello.cu CUDA program. It ran that program, and then it cleaned. It removed the binary file that was generated. So I'll get this output, and as well as the binary file hello, which was generated, will be removed. So I'm hoping that this is clear. Any questions? Okay, I guess there are no questions. Let me move further. Okay, so coming to the variables, instead of writing this names for the targets and prerequisites, what we can do is we can also declare the variable. So what we can do is we can name the variables like file1, file2, file3, or we can give any arbitrary name also. And then we can assign strings related to it. So please note that this assignment, this one should be string, and this colon equals to is an kind of an assignment operator. So this string hello is assigned to this variable file1, and similarly file2, it's to file2 we are assigning blah, and similarly for file3. And if you see, this program is exactly similar to what we did here, but the small change here is that we are using variables instead of hard-coded names, which are clean, blah, and hello. And how to reference this variable inside the makefile? We need to use this dollar and then curly braces, or dollar and this circular braces to or the normal parenthesis to reference this variables. So internally it is same as this this makefile. There is no change, but what it demonstrates is that we can use variables inside the makefiles, and it can be one of the examples on how to use the variables inside the makefiles. So it might make your code more readable. And so variables can only be string, and typically this colon equals to operator is used for assignment, and as I said, this dollar and then this curly parenthesis or this normal parenthesis are used for referencing the variables. And when we run the make and see the output, it will be exactly the same for this file. So I hope that this is clear. So let me see the questions. Okay, so I guess there are no questions. Let me make further. Okay, so sorry. Okay, so there is this all target, something called this all target. So what you can do using all target is that you can declare a single target. You can define a single target, and then you can specify multiple prerequisites to it. And inside it, you can write no commands, or it's simply just a combination of target and prerequisites, and there are no commands inside it. And what will happen when this this target or this rule is being evaluated? So it will see that I am I'm this all target, and I have this h1, h2, and h3 as prerequisites. So I can't run before this h1, h2, and h3 are finished. So this h1, h2, and h3 will be compiled and run. I mean, sorry, not compiled and run, but this h1, h2, h3 will be executed. That is, they will be the commands inside them will be executed. So this hello1, hello1.cu, hello2.cu, and hello3.cu will be compiled and run one after the another. And then once they are finished, will I mean this all target will be taken for the execution. But since it has no commands inside it, it will also finish. And then what we'll do is, what the execution will come here, which is at the clean target. And since clean target has no prerequisites, what it will do is it will remove this generated binary files, which is hello1, hello2, and hello3. So typically all target can be used for making the multiple targets run at the in the particular order. So here h1, h2, and h3 will be executed in that order, and for doing that we can use this all target. So I hope that it is clear that we can use all target for making multiple targets run at a particular time. So yeah, with this let's move ahead. So okay, one thing that I forgot to mention here is that this example also shows one more thing, right? That here we have just one target and multiple prerequisites. So this thing we have already seen in the previous, I think, no, I don't think that we have seen this, but yeah. So one point to observe here is that there can be multiple prerequisites as well as multiple targets. So this is the example that we have one target and multiple prerequisites, and until all these prerequisites are finished, we won't be executing the commands of this rule or this specified under this target. So I hope that this one is clear. Now let us come to this multiple target. So this is opposite to that what we saw right now. So here if you see this rule, this rule, here there are multiple targets actually and no prerequisites. So in the previous case there were multiple prerequisites and one target. Here there are multiple targets and no prerequisites, and then again we have all target. So so first of all we'll try to execute this one, and we'll see that compiler will see that it has dependencies on call1, call2, and call3. So call1, call2, and call3 will be run. So here please note that call1, call2, and call3 will be run one after the another, and first so when call1 will be called, it will run this algo1 and algo2, that is, it will compile it and then run it once. Then again for call2 it will be run second time, and for call3 it will be run third time. So this algo1 and algo2 will be compiled and run actually 3 times, one by call1, second time by call2, and third time by call3. And these calls are being made from this all target. So yeah, so they'll be run thrice. Each of this algorithm will be run thrice, this algo1 and algo2. And once that is finished, we'll reach this clean target. And what it will do is it will remove this binary files that are generated, which is algo1 and algo2, which are generated by compiling this algo1 and algo2.cu files. So I hope this is clear that yeah, that when there are multiple targets for a rule, the command will be run for each target. So here since there are multiple targets here, and since calls are made, here we are making calls for each each of these 3 of them. So commands which are there, which are written for this multiple targets, this is call1, call2, and call3, will be run for each of this call, that is call1, call2, and call3. So I hope that is clear that this will be run 3 times. this commands will be run 3 times. That is, they are run, so they will be run for each target, and here each target represents call 1, call 2, and call 3. Okay, let us move further. Okay, so let me see if there are any questions. There is some question with me. H1 has prerequisite H2, then will order of execution be H2, H1, H2, H3? I just missed the example where it was H1. Okay, you are talking about this. Okay, let me just quickly go back. If H1 has prerequisite H2, then will order of execution be H2, H1, H2, H3. Okay, so what H1 has prerequisite H2. Okay, in that case, first of all, H2 will be executed, and I think then H1 should be executed. Let me see what H1, H2, H1, H2, H3. I think H2 won't be executed. First H1 will be executed since it has prerequisite. So H1 will be executed, then H2, and then H3. So yeah, it's just H1, H2, H3. So okay, let me clarify this. So whenever okay, so let us take that example itself. Let's say that I think yeah, so okay, yeah, so let us say that here there was H2. So H1 had some prerequisite H2, which was this one, which was this target. So when that is the case, what will be the execution flow? So first of all target will be run, and it will see that I have dependency on H1, H2, and H3. So I just can't run right now. I need to first of all this H1, H2, H3 must be finished for me to run. So it will just first start running. First try to execute the commands that are there in H1. Now since H1 has prerequisite on H2, what will happen is this commands cannot run, right? So it will go to H2. So H2 will be run, and then H1, and then H3, and then all command will be run. I hope that is clear. So yeah, if I missed something, then you can type in the chat or you can unmute yourself. And
Sir, I had a doubt in this example itself. Like, won't H2 be run twice? Because like once as a prerequisite to H1 and once as a command in all.
okay, so assuming that you are, that example is that here we have H2. As far as I know, it should be executed once, but I need to check that. Probably I'll check this one and get back to you. But I don't think that mentioning prerequisite meaning that it should run twice. I need to check this. Probably, yeah, I'm not sure about this. If writing H2 here will make it run twice or not. Ideally, as per our example, if we are mentioning that in all target makes, I need to check this one. Probably I'll check this after the lecture, and we'll add in that Google group, or yeah, I'll reach. Um, I'll
Okay,
get
sir,
back to
sure.
you.
Yes,
Yeah.
sir, sure.
Yeah, so this part, I think this doubt is valid. I think Gokul's doubt is valid. Probably it might happen that H2 ends up executing twice. So I need to check this. I'll get back to you. Okay, so yeah, so I hope that this one is clear. This multiple targets is clear. That we can specify multiple targets, and based on the calls that are made, they'll be run each time whenever the call is made from the all command. All target, and yeah. Now that is, we saw this variables and multiple targets and all these things. So that is fine. But apart from that, we can also have conditions and loops inside the makefile. And yeah, how to use first of all we'll see how to use conditions inside the makefile. So first of all, yeah, so this if EQ and if not EQ are typically used for writing conditions. And yeah, like else is also there, like for branching and all those things. So let us say this example to understand it better. So we have declared this variable, right? Target CPU is x86, and we have set it to 1. And then what we are doing is we are checking if this target CPU is equals to x86 or not. So we are checking this value of variable. So probably I have this example is probably wrongly written, because if you see here the variable name here and here it is not matching. But okay, let us assume that there is some variable which is declared, and which is actually target CPU, target underscore CPU, and not target underscore CPU is x86. But yeah, let us assume that there is this variable target underscore CPU, and we are checking if its value is x86. If it is the case, then okay, I misunderstood it. So yeah, so there is this variable target underscore CPU which is there somewhere. Let us assume that it is there, and it stores the value of it stores the which type of CPU is it, it is in form of some string. And what we are doing is we are checking if that value is x86 or not. If it is the case, then we are setting this target CPU is x86 variable to 1. Variable to 1. And yeah, please note that we have declared this variable here. And if that is not the case, then we are checking if the target CPU variable is equals to x86 underscore 64. That is, it is 64-bit machine having x86. So if that is the case, then again we set this variable to 1, else we reset it to 0. So yeah, so at the end, if our CPU, this target CPU is x86, then this variable will be set to 1, else it will be 0. So this is one of the example using which we can uh, set this variable based on our target CPU. And yeah, so this typically demonstrates the usefulness of if conditions inside the makefile. And similarly, like if there is this if not equals to if eq, opposite to this if eq, there is if an eq, and this will this will compare this whatever is there here with here, and if they doesn't match, then it will print whatever is there, whatever statements are there here, else it will print this one. Not print, but it will execute this. Here in this case, it's echo statement, so it will print no. And yeah, here also it's echo statement. So here we have declared a variable, and there is some small error here. I should add column here. So like typical assignments should happen using this colon equals to. So this is wrong. So foo colon equals to some string. So I have assigned some string to foo, and then what I'm doing is that I'm checking if this foo is equals to okay, and it is actually not equals to okay, right? So this one will be executed, and the output will be foo not equals to okay, because foo is some string, it is not okay. So foo is not equals to okay will print it. And if that was not the case, if this was some string instead of okay, then it would have print no. Okay, so I am hoping that this conditions are conditions in makefile are okay. And yeah, similarly in that way we can also use loops inside the makefile. And for the there are the advantages of using this if and loops inside the makefile, and we'll see one use case related to it. But yeah, first of all, let us understand this loops also. So uh, let us say that you wanted to execute some code or some CUDA code that you compiled. Let's say it was algo.cu, and it generated the binary file which is algo, and you want to run this algo binary file with some random random inputs which are provided during command line, and this inputs that you wanted to provide to this algorithm were from 100 to 1000, and the way it is providing the inputs is like first of all you are giving 100, then 200, then 300, then so on till 1000. So this loop will start from 100. It will increase, it will go on increasing in the steps of 100. So first of all you will run this algorithm with input as 100 provided during the command line, and then it will be run with 200 as input, and so on till 1000. So this algo.cu is run with multiple inputs which are provided at runtime, or using command line. And what are those multiple inputs? That is, those are from 100 to 1000. 100, 200, 300, and so on till 1000. So yeah, this is one of the way in which you can use loops inside the makefile. And yeah, this was about the while loop. We can also use for loops inside the makefile, and for that syntax is very similar to the while loop, and for that you need to just specify the looping variable here, and then in is keyword, and then all this numbers that you want to for which you want to run the loop. So here algo will be run as with 32 as input, 100 and 900 as input. And yeah, so this is this is for the for loop. And yeah, I hope that these two examples are clear. And let me just quickly go to the chat. I guess there are no okay, so okay, so let us move on further, and let us see one complete example of a makefile where we can use all the things that we have learned so far. So yeah, so let us take this example. And there is a file called vertex removal. And that vertex removal, it's a CUDA file, and what it does is it does some it removes some vertex from some graph. And yeah, it is ran on multiple graphs. So let us say that we had this vertex removal.cu file in some directory, and in the same directory we had the test cases or the graphs on which we wanted to run this uh, vertex removal.cu file, and those graphs were in the zip file. And so first we need to unzip those files. So let us see step by step what will happen. So okay, so here main thing that we want to do is we want to run this CUDA program, which is vertex removal.cu, on the graphs, multiple graphs. And to automate this process, we can write a makefile corresponding to it. And let us see how to write the makefile. So first of all, we are writing this all command, which is dependent on vertex removal. So and yeah, and this vertex removal has no dependency. So what it will do is it will first of all compile. So what it is doing is, since it has no dependency, it will run its command. And what command it will run? It is compiling this vertex removal .cu file, and it is storing its binary into vertex removal as a vertex removal file name. So once we have compiled it and we have this binary, which is vertex removal, we can run this commands, right? This set of commands, and which is part of the all target. So what we'll do here is that we'll as I told, we want to run this vertex removal on the set of graphs, and these graphs are there inside this bench.zip, which is some zip file. So we'll unzip that file, and we'll move the all the test case which are generated in some test case folder, which is there. I assume that there is some folder, test case folder, and we are moving all these files that are generated, not generated, but that are unzipped into that uh, uh, that folder. Not sorry, I think I missed something here. Yeah, yeah, I'm correct. So yeah, so this zip file was there inside this example folder. It was there inside example test cases and test.zip. So from there we are unzipping it, and we are moving all the unzipped file into our current directory. So okay, so it is something like this. So yeah, so in the current directory we are having this vertex removal.cu, and apart from that, I think there was nothing inside this current directory. And this test benches, or the test cases on which we wanted to run this file, where they are in examples test case and test bench.zip. So we are unzipping that file and moving all the unzipped file into the current directory, which is shown here. And then after that, what we are doing is we are running the loop, that is the number is the looping variable, and we are running the loop from 1 to 10. That is, it will be run from 1 to 9, so it is less than so it is less than or equals to, so it will be run from 1 to 10. And for each iteration of while loop, what we are doing is we are um, running a particular test case, if you see. So this t then number dot mtx is some graph file format. So what is happening is we are running this binary file, which is generated here, on a particular test case, and that test case is determined by this number. So I hope you are getting this. So so during first iteration, which test case will be run? It will be t1.mtx. So during first iteration, this number will be replaced by 1, and yeah, so this /vertex removal t1.mtx will happen, and whatever output it is generating, it will be dumped into this vrgraph underscore 1.txt. So this entire thing, actually, let me write this. It will be like this. So in first iteration, this thing will happen. So this /vertex removal will be ran on t1.mtx, which is some graph, some test case, which was there in that zip file, which we unzipped it, and then we ran this, and the output will be stored in this, and this will go on. And yeah, so, and what we are doing here is that we are also using this if conditions here, if else conditions here. And what we are doing with this if else condition, we are checking if that number is 4, then we are skipping the number by 2. So we are not running the test case number 5. So if you see this execution pattern, you'll see that the test cases on which we are running the program are 1 to 4, and then from 6 to 10, and we are skipping the 5 because the number of test cases in this bench.zip were having this inside this t5.zip was t5.mtx was missing, and hence, to ensure that this t5 is not t5 is not run, the execution of t5 is skipped, we have written this if else condition to make sure that it is not run on it. So after 4, this number will jump to 6. So yeah, so T1, T2, T3, T4 will be executed. This vertex removal will be executed on T1, T2, T3, T4, and then T6, T7, T8, T9, and T10. And all the results that are generated by running this vertex removal on that particular test case will be stored in this VR graph in that particular number. So I hope that you are getting a flavor of how to use a makefile to automate the execution of the CUDA program. So this is a very simple example that I used for running some CUDA program on multiple test cases, and to check what are the results, and so on. And if you see, everything is automated here, so you just don't need to run each thing one by one. And yeah, so that is the beauty of the makefile, that if you have multiple dependencies and you have this repeated execution of your CUDA program on multiple test cases, then you can just automate using makefile. And yeah, this is very, this makefile will come very handy when you are working with large projects. It might be a CUDA project or something else also. So yeah, any questions after this? Okay, I think there is one question. Could you say what this minus LE is? Okay, so yeah, sorry about that, but this L is less than or equals to. So while this number, which is initialized to 1, so this number is just a variable, and again I have forgot to this problem. Okay, yeah, this number is just a variable, and uh, until it is less than 10, what we are doing is okay, so this minus L is less than or equals to, so until it is less than or equals to 10, what we are doing is we are running this while loop. So from 1 to 10 we are running the while loop. So I hope that is clear. This minus L is just less than or equals to, it's kind of a that this this thing that we used to write in normal loops, right? Okay, I hope that it is clear. And yeah, we are skipping the number 5 because we are doing number plus equals to 2 when number is 4. Any confusions or questions up till this point? Otherwise, we'll start with debugging and profiling, which might take some time. Okay, I am assuming that there are no questions. So okay, so let us start with debugging. So yeah, in general, uh, debugging the parallel programs is difficult because there is no there is no determinism involved in the parallel program. So in sequential program we know the order of execution, that this will be executed, then this, and then this. But in parallel program, since multiple threads are executing the multiple instructions, so there can be arbitrary interleaving and the outputs can be different. So let us understand this with an example. So let us say that you have a triple SPA application, right? That single source shortest path application. So in that case, let us say that there were multiple paths that were multiple shortest path from one source to that destination. And since there are multiple possible paths which are shortest actually, so uh, the output or the value of the shortest distance will be same, but uh, the shortest path that is calculated by the algorithm, or the actual path which is used for moving from the source to destination, which is the shortest one, can be different. It can be different if we run on the parallel if we run on such parallel hardware like GPU. So it might happen that there can be a different interleavings of the thread, and based on that the output or the shortest path that we get might be different. So I hope you are getting this point, that uh, the value of the shortest distance will be same, but since there are multiple shortest paths with the same that shortest distance value, based on the interleaving or the execution of the thread, there can be there can be different shortest distance possible. So this can so this non-determinism is possible while executing this parallel programs, and since the output can be different, the debugging can be quite challenging during for the parallel programs. And yeah, so in general, the debugging of parallel program is difficult, and we'll see how to debug them using this cuda-gdb. And one more point is that there can be multiple intermediate values also, and this number can be really very large. So let us say that you are running your algorithm on a very huge data, then the number of intermediate steps, or the number of intermediate steps that it might go through will be very it might generate will be the number of intermediate steps that it generate might be very large, and hence debugging will be very challenging. So yeah, and yeah, so let us come to this cuda-gdb. So it is used for debugging the CUDA programs which are running on real hardware, which is our GPU, and it is just an extension to the GDB. So GDB is used for debugging our C programs, and it's just a extension. cuda-gdb is just an extension to the GDB, and it allows this multiple things like breakpoints and single steps and read-write memory contents. That is, what are the value of the variables and so on. And yeah, we'll see these things in the upcoming slides. Okay, so let us take one example. So yeah, let us see this program. So we are including standard header files here, and then we have this kernel in which we are passing some pointer. I mean, it is just an integer pointer which will hold some address, and then we are initializing this. We are first of all we are dereferencing this pointer x, and we are assigning the value 0 to it. And then inside main, what we are doing is we are declaring a pointer, passing this pointer to the kernel. And yeah, we are launching this kernel with 2 comma 10, I mean 2 comma 10, which is 2 blocks and 10 threads in each block. And then we are using CUDA device synchronize. So if you see here, the error that I mean the mistake that we are doing here is obvious, right? So we have declared pointer, but we have not done CUDA malloc. Declaring pointer is okay, but this pointer should point to some valid memory location that is on the GPU, right? That is that part we are missing here, right? That this x should point to some valid memory location on the GPU, and that part should be done using CUDA malloc and assigning the allocated address of the allocated memory to this pointer, and that part we are missing. So okay, so that is fine, and that is the mistake that we are doing. And how can we debug this program? So one way is to write the printf and check, I mean printf and check what will happen. So first of all, one thing that we should observe is that when we'll try to run this program, it might lead to a seg fault, because we are trying to dereference a location that is not, I mean, this x might point to some random memory location, it might point to null, and if we try to dereference the null, it is null pointer dereferencing, and it might lead to seg fault. So yeah, so this program might crash, is what I'm telling. And if it crashes, then we'll try to debug it, and one of the way to debug it is we can write printf. But when we write this printf, it might not print anything, because yeah, because this program already crashed here, and then the kernel will return, and it will just I mean CPU will just continue its execution after CDS. So okay, so in order to get the insight what is happening here, what we can do is, instead of just using this printf, which actually doesn't print anything in this case, and actually it's a bad way of debugging a program, writing a printf, what we can do is we can use this this function that is available in CUDA, that is CUDA get last error. So what this function does is it returns the last error that was reported by this CUDA kernel. So please note that whatever error that is occurring inside this kernel might not be reported back to CPU, since this error is being, I mean, this null pointer dereferencing is happening on the GPU. It might not report back to CPU, and that's why we might not know what is actually going on. So in order to know that, we have this function CUDA get last error, and what it will do is it will tell you the last error that was reported, I mean, which was reported by this CUDA kernel K, and it will be stored inside this variable err, which is of type CUDA error t, which is CUDA error type. And what okay, so, and to print what the error was, I mean what the error which was reported by this CUDA get last error, we need to pass this variable arr to this CUDA get error name and CUDA get error string. So it will print the name and string corresponding to that error. So here the error code was 77, which was printed by this err. So this err is some, consider it as some unsigned integer. So err was 77, and error name corresponding to this 77 number was CUDA error illegal address. So it is saying that you are trying to access some illegal address. So which is actually correct, right? This since we are not initializing this, I mean, since this x might point to null, and we are not initializing any memory location and making it point to this pointer x, it might happen that it is pointing to null, and we are, since we are doing null pointer dereferencing here, well, it should actually throw this CUDA error illegal address, and that is what it is. This CUDA get last error is trying to suggest us. And then this CUDA get error string, what it is printing is that an illegal memory access was encountered. So It's trying to tell us that you are trying to access some illegal memory location. Okay, so these are the multiple error codes corresponding to multiple error codes corresponding to different types of errors. So 0 represents CUDA success, that there was no error. Then there are different kinds of error, like there's this 10 corresponds to that you are using some invalid device. That is, you are trying to reference to some GPU which is not already there. And then this 9 represents this invalid configuration, that probably you are launching kernel with some invalid configuration and so on. So what you can do is you can try to write a program to invoke each and every type of this error from 0 to 10, and I'll leave this as homework for you people. Okay, so yeah, so this was one of the way to check what is the error that is being reported by the kernel. But more better way to do, more better way to debug the CUDA program is to use cuda-gdb, and it is very similar to the GDB that we have for debugging the C program. And yeah, first of all, let me see if there are any questions in the chat. I think there are no questions. Okay, so in that case, let us move further. So okay, so yeah, so one of the good way to debug the CUDA program is using cuda-gdb, and yeah, so how can we uh, debug our programs using cuda-gdb? So we need to compile it using this minus small g and minus capital G flag. So this small g represents that we need to compile this C programs, and this capital G represents that we want to compile the CUDA programs. So please note that since CUDA is some sort of an extension to the C, we can always debug C programs using cuda-gdb. So this minus G flag shows that we are compiling these normal C programs, and we are debugging the normal C programs, and minus G capital G represents that we want to debug the GPU specific part of the CUDA program. So okay, so yeah, and then once the binary file is generated, so this compilation will, with this minus G and small g and minus capital G flag, will generate the binary file corresponding to this file.cu CUDA file. Then we need to run this generated binary file, which is a.out, using this cuda-gdb, and then it will and then in the prompt we need to type run, and then it will start running from the first instruction in the main, and yeah, and it will stop at the point where it might encounter some error. And yeah, that is how we can pinpoint that what's going wrong in here, and then this GDB will print the information corresponding to it. We'll see in the later slides. And one more point to note here is that since CUDA program might be running with the large number of threads, uh, this cuda-gdb has provided some notion of focus, that is, we can focus on a particular warp or a particular thread block or particular set of threads and so on. So we can switch our focus to these things, that is a particular thread or a particular warp or a particular thread block or so on, or even a particular kernel or a particular grid. Okay, so let us see one example related to this cuda-gdb. So yeah, this is the same kernel that we were having, right? That we were doing this null pointer dereferencing here, right? That this x was declared as a pointer, but on the CPU, but we were not assigning a proper address to it. That is, it was not being assigned the address corresponding to any of the GPU memory location, and hence there can be a null pointer dereferencing here. So let us assume that we have compiled our program using this flags, and then we ran ran the cuda-gdb using by typing this run here, and then cuda-gdb starts running this a.out binary file, and then what it is saying that yeah, it is running the threads, and this LWP is lightweight process, which is actually threads, and then it is saying that there is some CUDA exception, which is device illegal address was encountered, and then it is giving details related to it, that this program received signal CUDA exception underscore 10, that is device illegal address. And where did it encounter this error? That is at the line number 6 here. And what was at the line number 6? This printf statement was there, and there it encountered the error. And if you see here, it is also showing the kernel launch configuration, that we launched the kernel with 2 thread blocks. So here please note that 2 comma 1 comma 1, it is showing it is showing all the 3 dimensions that we have learned in the computation lecture, right? That there are 3 dimensions to the grid and 3 dimensions to the thread block. So here uh, we have 2 thread blocks and we have only just x dimension. So if you remember here, we are launching it as 2 comma 10. So here we have only just x dimension for grid and thread block. Y and z dimensions are 1. So it is showing that this is the kernel launch configuration, and the uh, pointer x is initially pointing. So this x was pointer, and if you remember here, we were passing it as the argument here, and the value of that the value of that pointer x is initialized to 0. So this is kind of a good indication to me that since this value of the address which was pointed by x was 0, and since I'm doing this star x here in the printf, I'm trying to dereference the null pointer, and it will definitely give me null pointer dereferencing error or the runtime error. And could I think that it's trying to access some illegal address, and that is what it is actually. So I can understand from this entire thing that it is trying to access some illegal memory location, and where it is happening, it is happening somewhere here. And yeah, apart from that, it is also printing some information related to the grid and thread block where it is currently trying to focus. So it is saying that I'm at kernel 0, grid 1, and this block and thread number 0. And I'm running currently on device 0, which is the 0th GPU, and on streaming multiprocessor 13, and on warp 0 and lane 0. So lane is a particular thread. Okay, so any questions up till this point? I guess there are no questions. Let's move further. Okay, so yeah, so for cuda-gdb, we can using cuda-gdb we can also print information related to kernels. So when I type this info CUDA kernels, it will give the information related to the kernels or all the kernels that are there or that are currently running. So it is printing that this kernel 0 has no parent, and what is this dev? I don't know this. What is this dev? But yeah, it is having. It has it has grid number as 1. It is currently active. It is probably running on this streaming multiprocessor, which is its SM mask, and then it has this grid dimension, it has this block dimension, and yeah, this is its invocation. This is its invocation. This is the way it is being invoked. So k is the name of kernel, and x is the argument that we are passing, and its initial value is 0, which is 0x0. In hexadecimal, it is 0. So yeah, this will give us some information related to the CUDA kernels, and this info CUDA kernels, this info CUDA kernels instruction. And then there is this info threads, which will give us information related to the threads which are currently running. And if you see, it is giving some information that this thread, which is numbered, this one, which is part of this a.out, and it is using this libc.so.6. And yeah, so it is currently saying that there are 3 threads, thread 1, thread 2, and thread 3. And yeah, if you see, for this example, we were launching 20 threads. There were two thread blocks with 10 threads, and but if you see here, it is just giving information related to 3 threads. And why it is so? Because it is not actually showing the information related to the CPU threads. That is sorry, GPU threads. That is showing the information related to the CPU threads. So uh, yeah, so these three threads are CPU threads, and since we are invoking it using info threads, it is showing the information related to the CPU threads instead of GPU threads. And in order to print the information related to the GPU threads, we need to use this info CUDA threads instead of this info threads. And by doing that, we'll get the information related to the threads which were part of that kernel which we launched, right, using 20 threads. So yeah, so this is the information related to this uh, 20 threads that were part of this that kernel. So if you see here, it is saying that uh, yeah, so it has two thread blocks, which is 0 and 1, and each thread block has 9 threads, and total count of the threads which are part of this kernel is 20, and then this is the program counter corresponding to that them, and there is uh, there is this file name corresponding to them, and the line number is probably the line number that they that way I mean that is the line number where they halted, which is line number 6 is the line number where this error was there, if you remember. And yeah, so this is how we can print the information for each thread using this info CUDA threads. And yeah, apart from that, we can check what is the current focus of a particular what is the current focus of the cuda-gdb using this command cuda kernel block thread. So it will say that currently I'm focusing on kernel 0, block 0, and thread 0. And in order to change the or switch the focus, what we can do is we can specify the block and thread we want to, to which we want to switch the focus. So cuda block 1 thread 0 will help us in switching the focus from 0 block 0 thread of the kernel 0 to block 1 0 thread of the kernel 0. So here it is saying that now focus is switched to the kernel 0, grid 1, block 1, and thread 0. And then it is giving some information related to the device on which it is executing, streaming multiprocessor, and so on. Yeah, and then again, if you type this CUDA kernel block thread, it will say that it is now executing. It is now focused on kernel 0, block 1, and thread 0. Since we have there, since we have done this focus switching, it is now showing us the appropriate information. Okay, so apart from this, you can also specify breakpoints in your file which you want to debug. So you can tell that the breakpoint should be the first instruction of the make using this break make main break main instruction. So what it will do is as soon as it reaches the beginning first instruction of the main function, it will start executing step by step. So that is what is the breakpoint. And also you can specify the breakpoint using you can also specify the breakpoint as a line number. So here what we have done is we have specified break file.cu :223. So in this file.cu, the breakpoint is inserted at line number 223, and as soon as the the flow will reach at that line, it will start executing in step-by-step manner, and will show the information related to each and every step that are being executed by that cuda-gdb, and it will show the information related to the variables and all the states and which are being modified by by execution of each and every statement in cuda-gdb. By the execution of each and every instruction in that program. And then there is this set and you can also set the breakpoint using this cuda break on launch application. So what it will do is this statement will do is it will add breakpoint at each during each entry of the kernel. So during during the execution of the kernel, the there will be one breakpoint. I mean, at the beginning of the kernel, there will be one breakpoint, and as soon as the kernel execution will begin, we'll be able to see the step-by-step details of what all is changing and so on. And yeah, you can be also be very specific in inserting the breakpoint. So you can write this thing, that break for file.cu at line 23 if the thread ID is 1 and if the value of I is less than or equals to 5, and yeah, less than 5. So this is called as conditional breakpoint, and if this condition satisfied, then there will be breakpoint inserted, and for all the threads, here in this case it's just one thread, so for that thread all the debugging information will be printed. Okay, and after inserting the breakpoint, once you have inserted the breakpoint, you can see the step-by-step execution by using this step or by pressing the enter. And yeah, it will show you each and every detailed information for each and every uh, I mean detailed execution for each and every instruction that are being executed inside that program. Okay, so apart from that, there is this I mean, we have seen this thing, right? Info threads, info apart from that, we have seen this info threads and info CUDA threads, and apart from that, yeah, info kernels, info CUDA kernels we have seen, info CUDA kernels, info CUDA threads, and then there is this thing, info CUDA SMs. So this can be used to get the information related to the streaming multiprocessor. So we can get the information related to the streaming multiprocessor using this instruction, and what it prints is that which streaming multiprocessor are currently being used. So if you see here, 13 and 14 streaming multiprocessor number 13 and 14 are being currently assigned with some threads. So if you remember, we had launched kernel with 2 thread blocks, and each thread block were having 10 threads, and yeah, so that thread block number, okay, so there were two thread blocks. So one thread block was assigned to this 14th streaming multiprocessor, and 13th second thread block was assigned to this 13th streaming multiprocessor. So yeah, I hope that this is clear, that it is printing all the streaming multiprocessor and currently which is being occupied and which is not being occupied, and yeah, so yeah, and apart from this information related to the kernel warps streaming multiprocessor, you can, yeah, kernel thread streaming multiprocessor, you can also print the information related to the warps using info CUDA warps, and yeah, it will again print all the information related with the particular warp. So there were 2 warps, right? And first warp was going to streaming multiprocessor number 14, if you see here, and the second warp is going to the streaming multiprocessor number 13. So 2 thread blocks, each having 1 warp. One warp is, first warp is going to 14, second streaming multiprocessor 14, second is going to streaming multiprocessor 13, and when we do this CUDA info CUDA warps, it will show that information related to the warp. So here it is saying that on device 0 on streaming multiprocessor 14, this warp is, there is some warp, and the information related to it is printed here. So yeah, so typically the block ID is printed, and then which thread is active and so on, and then thread ID is printed and so on, then there is some mask and all those things are also printed. So yeah, that is the information related to the warps, and you can try uh, you can try to see the multiple things related to it, like warp. This, I think this is some ID related to the warp or some device or something, and then this is this uh, what is this lane number and mask number and so on. Okay, so apart from that, you can also get the information related to each and every thread using this command, which is info CUDA lane. So this lane is actually related to the thread. So when you type this info CUDA lane, it will give information related to each and every thread. So if you remember, there were 10 threads in each block, right? So, and the IDs were going from 0 to 9. So on streaming multiprocessor 14, there was one block assigned, there was one thread block assigned to it, and that thread block was having 10 threads inside it, and the information related to that 10 thread block is being printed here. And there is this, I think, program counter. I think this one is the program counter, and then there is this thread ID, and then this device or something is there, and then there is this, yeah, and then it is printing that it is accessing illegal address, device illegal address, because we were trying to do that star. I mean, we are trying to dereference the null pointer, right? So it is saying that the exception that it is facing is this device illegal address, and yeah, so you can get information related to each and every thread that is being currently executed using info cuda links. And as a homework, you can try to see what what sequence of steps you should perform using this cuda-gdb, or what commands that you should run on cuda-gdb to identify the error in this program. And yeah, this program is having this dangling pointer exception, and you can try to see how to get that how to catch that error using cuda-gdb. Okay, any questions at this point? Okay, if you have any questions, then please feel free to ask, or else I'll just move on. Okay, so we'll briefly touch upon the profiling part. So profiling is typically useful when we want to measure the performance of our CUDA program. So in order to time our kernels, you can use profiling. And yeah, apart from that, there are also other ways in which, or other indicators of the performance, like how much memory you are utilizing, how much cache misses are happening, and all those things, and what is the degree of divergence, and what is degree of coalescing, and all those things, which indirectly shows the which indirectly shows the performance of your CUDA program. And all this you can do it, all this you can check, or all this you can keep track of using nvprof, which is a profiler, this kind of profiler provided by the CUDA. And there are two types. There are this intrusive and non-intrusive thing, which says that when you need to change your program in order to profile it, then it's kind of an intrusive profiling, because you are adding additional statements in your program in order to check its performance, or in order to get some insights from it. So that is intrusive. And non-intrusive is the case when you just don't need to add any additional statements inside your code in order to get the information, like timings and all those things. Like, so in order to time your kernel or any of the CUDA program, what you can do is you can also use some inbuilt functions, like that get time of day and so on. So you can insert those statements inside your CUDA kernel, and that will become intrusive, right? Because you are adding the statements inside your, you are adding the instructions inside your CUDA program to for the timing, or checking the time of your kernels. But the other ways to, another way is non-intrusive. That is, you just don't you just don't need to add any instructions, additional instructions. This profilers that is nvprof and nvsite and all those things will help you in checking the performance of your CUDA program. So let us see one example, and then we'll probably end this class. So so again, as I said, this nvprof is non-intrusive. That is, you just don't need to add any extra statements inside your CUDA program in order to get the performance details. So no change required to the binary file, or the input file, input CUDA file. And the way you need to run it is that you need to use this nvprof and then specify the binary file that you want to profile. And then you need to use this in order to profile the parts of the programs, you need to use this CUDA profiler start and stop instructions. And you also need to use this API inside your CUDA program, that is CUDA profiler API.h. So you need to include this, and you probably might need to include this instructions in your programs. And yeah, so nvprof, if you want to program the you want to profile the part of your program, then you need to use this profile, this flags, which is profile from start and off, and then you need to provide this binary file. So let us look one example related to this. So this is the CUDA, typical CUDA program that we want to profile. And if you see, there are three kernels here. One is this K1, K2, second is K2, and third is K3. And this kernels are being invoked multiple number of times. That is, each one is being invoked 100 times. And yeah, and we want to know which kernel we should optimize in order to get the performance benefit, or which kernel consumes the most time. So this thing can be done very swiftly using this nvprof. So you just compile this CUDA program and uh, run this binary file using nvprof, and it will give you some indication of the performance. That is, uh, what time each and every kernel is taking. So you'll see that 39% of time is taken by K1, K2. 33% of the total time is taken by K3, and 26% of the total time is K1. So from this information, you just understand that K2 is the most time consuming kernel, and yes, it must be, since it is using atomics. So yeah, so K2 is the time consuming, and you should be, you should first try to profile, not profile, you should first try to optimize K2, and then K3, and then K1. And what else it is saying, that this yeah, that this 95% of the total time is taken by the kernel, kernel launch, that is CUDA kernel launch. So, and that is quite intuitive, right? Since we are calling the kernel 100 times, each kernel 100 times, and total there are 300 calls. So kernel invocation, that is, so if you see here, the calls are 300. It will take some time, and that is that is totally taking 95% of the total execution time of the program. So I hope you are getting the flavor of it, that you can use this nvprof to get some detail about the performance related to your CUDA program, and it will give you a very detailed overview of what's going on. And yeah, so let us move further. Yeah, so let us conclude the nvprof with this slide. So nvprof provides device specific profiling. So you can get device specific profiling for a particular device. You can get uh, a detail of you can get a performance details specific to a particular device. You can also use remote profiling. That is, the program is being ran on some particular device, and GUI is somewhere else, and you want to profile it. And if you want to profile the program, then you can do it using nvprof. And yeah, and the last point is that it will dump all the files, all the output in the CSV as a CSV file, and you can check that file and see the details related to it, related to your CUDA program. Yeah, so I hope that this example and this points were clear. If there are any questions, then please feel free to ask. Otherwise, I think this was the last slide I have, and if there are any questions, then please feel free to ask, else we'll call it a day and we'll disperse.